Hi there, I'm Clément Roblot. Today we're gonna have a look at some teardown. I got those two battery chargers, one of them connects through USB, the other one directly connects into the wall. And I suspect that one to be a lot better than this one, but I really like the idea of having a USB one. So I'd like to open them and have a look at how they work inside. This one feels dodgy to me, and I'd like to know how it does its magic and if it's reliable or not. I cannot trust that one just by the brand and the fact that it's working perfectly fine. Let's open them and see what's inside. So I'm gonna open that one. Yes, indeed that is a small circuit. And yeah, as expected, there isn't anything much in it. Just one diode, two resistors and an LED. That's indeed a bit light for managing the charge of a battery. I suppose that they are doing some kind of a divider bridge, and the diode is there to make sure that everything is plugged the right way. But that's it, and that explains why my batteries that I get in never seem to stop charging. The way to detect if they are charged or not is to touch them and see if they are hot, then it means that they are charged. If they are still cold, then still need to wait. Okay, that is indeed disappointingly small. Let's open the other one and see if they do better than this one. There we go. Yes, indeed, a lot more is happening in here. So first of all, we got our batteries that we can plug here, and here we're gonna have the 220 volts that arrived. So obviously a lot more is gonna happen just by the fact that you need to convert 220 volt to something reasonable and DC for your batteries. So we can see some kind of a small inductor and some larger caps for your decoupling caps. You can see the 4 diodes for the full bridge rectifier. And so, yes, we're gonna have our primary part of the PCB. It's gonna handle the high voltage part with, I suppose that IC is gonna be some kind of a PMIC to control that electric conversion. And then that's gonna be the secondary part that is gonna be comparable to the shitty USB one that we got there. But even that part is a lot more complex, and it even involves some kind of an IC. And if we look at it, it's actually the EM78P143, which is technically an extremely small microcontroller. Also on that one, we can see some components like these ones and these ones that could potentially be some MOSFETs or some kind of a transistor that would indicate that the device is able to detect the charge level of our battery and to actually cut the charging of the battery. Which is what we want. We'd like to keep our batteries charged but not to overcharge them. So, as we see, one of them is really shit and one of them is seemingly actually good. Knowing the brand, that should indeed be good. Now, I'm not going to go more in details reverse engineering those devices. I just wanted to know which one to use and which one to not use. I love the idea of using USB, but in those conditions, I'd rather not. Some points that could be interesting for you on that PCB is going to be, for example, that microcontroller comes from a brand that I have no idea before, Elan, never heard of them before. They are doing here an 8-bit microcontroller, which obviously is most certainly not going to be ARM. We are used to seeing ARM-based microcontrollers everywhere nowadays, but something to keep in mind is that you need to pay for the ARM license every time you buy a microcontroller, which is going to be certainly within a few cents, but still, when you're producing some device at a very large scale, you're gonna try to save as much as possible, and every cent counts, every fraction of a cent counts actually. So that's why in some cases you might see some weird microcontrollers that seem to be very complicated to work with, but they are most certainly a lot cheaper than an ARM-based microcontroller, for example. Another point that if you look on that device, you're gonna see that a lot of those resistors are having the same values, 220, 220, 220, 220, 220 here also. And most certainly, a lot of them are actually doubled. For example, those ones seems to be in parallel, and those ones in parallel. That's a trick for, once again, high volume production, where instead of having many components in your PCB, you're gonna do BOM consolidation, or you're gonna try to reuse the same components, including in some cases even you're gonna allow to use the resistor 2 times instead of another one time, which allows you to buy a lot more resistors of the same type from the same constructor, which is going to give you more leverage when negotiating the prices. But also, very importantly, that means that you got less parts that could be in shortage when you're producing your devices. And part shortage are actually a big issue nowadays. So having only 10 different components instead of 15 means that you've reduced technically by 30% the risk of shortages on your devices. Finally, another thing that can be interesting is going to be that dot, which is called the fiduciary, which is there for when your PCB is on the conveyor belt to be assembled, for a camera to look and identify that spot and be able to align on it and be more precise when it comes to placing the components. That's all that I see being really remarkable on that PCB. Although you can notice that there is only one layer, which seems also archaic. Nowadays everybody is able to do 2 layers for cheap, but once again, when you're doing high volume production, each layer count, each cent count, and being able to produce your PCB on only 1 layer, well, that's actually some penny saved, which is always good to take. I think that's all on that subject. I'm gonna keep using that one, and this one is gonna go most certainly in the garbage. See you! Yeah.
It's not blur because of overheating, it's blur because you didn't configure it.